Good morning once again, and welcome to another episode of The Angry Astronaut. Yesterday I had an opportunity to visit an online friend of mine, a guy who's been a strong supporter of my channel for quite a long period of time, and he works at a nuclear reactor in Suffolk called the Sizewell Nuclear Reactor. And so I had some ideas in mind in terms of learning a little bit more about nuclear power, about radiation shielding, that sort of thing, in order to gain a better perspective on what our astronauts are really going to be facing when they delve into the domain of interplanetary travel, or indeed even going to the moon. And let me tell you, it's not a pretty situation at all. Now, we are very fortunate here on this planet. We have a thick insulating atmosphere that alone actually provides more than enough protection from the sun's radiation. We actually don't even need a magnetic field, in spite of what certain science fiction movies might tell you about the consequences of losing our magnetic field. That's something that wouldn't happen at all. Our atmosphere provides a tremendous amount of protection. We're talking meters and meters of solid concrete is the equivalent of what our atmosphere does for us. So solar radiation wouldn't be a problem even without a magnetic field for a while. But over time, without a magnetic field, of course, solar radiation would strip away our atmosphere, and then we'd really be screwed like people would be on Mars. But even Mars isn't as bad as one might think. Really, the biggest problem that we're going to face when it comes to radiation is not the radiation on Mars, but the radiation on the journey from here to Mars, or the radiation that's going to exist on the moon, because believe it or not, Mars' thin atmosphere actually provides a substantial amount of protection to future colonists. Not, a lot of protection. Certainly they're going to need other methods, but still, it is a very different sort of environment. The place where things are really going to be dangerous is on the journey from here to our destination. And believe it or not, nuclear power can actually help us rather than hinder us when we're talking about that journey. We're going to find out all about that in just a moment. Now, first and foremost, I want to offer my deep, deep thanks to a fellow who goes by the name of Framrick on Discord and online. As I say, he's been a longtime supporter of my channel. He's a nuclear physicist who works at the Sizewell Nuclear Power Plant. When we're talking about radiation shielding and the long-term effects of radiation, I don't think there's a better expert on the planet. This guy specializes in protecting human beings from radiation. He has worked at this power plant since he was 19 years old, and he's in his 50s now. And in that time, he has actually accumulated less radiation than if he worked as a flight attendant. Yes, you really don't get a whole lot of radiation at one of these reactors, and it actually provides almost 1/20th of the UK's entire power needs, which means if you had 20 of these reactors, the UK wouldn't need any sort of energy imports whatsoever. Their problems would be over. And when it comes down to it, this reactor has never had an accident. The UK is not vulnerable to these kinds of accidents. No tsunamis, no earthquakes, no real hurricanes, nothing that would cause something, as devastating as Fukushima, for example. So I mean, it is a logical solution to the green energy crisis. It's expensive, though. We're talking billions and billions of dollars to build one of these reactors. And of course, there are many, many safety protocols that have to be implemented with one of them. But still, it was an eye-opener. I also got to see where the reactor takes in its water, the water intake that is from the Atlantic, or rather from the channel, I guess, and also where the water comes back out. And that's amazing as well, because I learned that in spite of all of the radiation that this water gets exposed to, the water itself does not become radioactive. As a matter of fact, when it's flushed back out into the ocean, the only environmental impact it has is that it's a few degrees warmer, which means fish really like where it's coming out. Very warm attracts lots of food to the area for them, and therefore attracts lots and lots of fish and the things that feed off of them. That's the only environmental consequence of this process. Amazing stuff. And we're going to learn about the benefits of water to interplanetary travel here in just a second. But first, let's talk about the types of radiation that astronauts are going to be facing in space. It's different from the types of radiation we experience here on Earth. It's comprised of atoms in which electrons have been stripped away as the atom accelerated in interstellar space to speeds approaching the speed of light, galactic cosmic rays as it is often called. But it's made up of three kinds of radiation: particles trapped in the Earth's magnetic field, particles shot into space during solar flares, and finally galactic cosmic rays, which are high-energy protons and heavy ions from outside our solar system. All of these kinds of space radiation represent ionizing radiation. Now, ionizing radiation is especially dangerous. Non-ionizing radiation, such as UV radiation, can be problematic, but it can also be shielded out by some simple sunscreen, for example. But ionizing radiation has the ability to move through substances and even alter them as it passes through. When this happens, it ionizes the atoms in the surrounding material with which it interacts. Ionizing radiation is like an atomic scale cannonball that blasts through material, leaving significant damage behind. More damage can also be created by secondary particles that are propelled into motion by the primary radiation particle. Now, galactic cosmic radiation is the worst of these, and the prominent thing that we're going to have to deal with. It comes from outside the solar system, primarily from within our own galaxy, but not all of it. Some of this actually travels between galaxies. It's the nuclei of atoms that have had their surrounding electrons stripped away and are traveling nearly at the speed of light. Another way to look at this is to imagine the nucleus of any element in the periodic table, from hydrogen to uranium. Now imagine that same nucleus moving at incredibly high speed. The high-speed nucleus is GCR, or galactic cosmic radiation. These particles were probably accelerated within the last few million years by magnetic fields of supernova remnants, but really, we're not certain what caused it. But one thing is certain: astronauts exposed to galactic cosmic rays in interplanetary space, or indeed even on the moon, are going to be soaking up a lot of radiation unless they have lots of protection. And things like stainless steel are not going to provide enough shielding. As a matter of fact, it could make it even worse. Galactic cosmic rays, when they pass through metal, can actually split off into their component elements, giving off X-rays in the process. In other words, creating more radiation. So you need a lot more than steel or aluminum. Now, for sake of comparison, let's look at the surface conditions on Mars as have been read by Curiosity's various radiation meters. The number of REMs per year that one can accumulate on Mars is really not that bad. It takes 100 REMs to add up to 1 sievert. Yes, there's lots of different ways to refer to radiation. Sieverts, REMs, and also grays. Grays referring to the amount of damage that the radiation does when it impacts living tissue. So 20 rems per year, which is as bad as it gets, it would take 5 years to accumulate into 1 sievert, which is the maximum amount that NASA recommends for astronauts, which means if an astronaut goes to Mars for a couple of years and is unlucky enough to be in a high radiation zone, he's only going to accumulate 4/10 of 1 sievert. That's still quite a bit in 2 years, but nothing compared to how much he's going to get in space. That is the radioactive wasteland, not Mars. And in space, like on the Lunar Gateway, for example, things are going to be a lot worse. For example, if you were to stay on the Lunar Gateway for a year, you would soak up almost half a sievert, 50% of what NASA regards as being relatively safe for astronauts for an entire lifetime in 1 year. We're talking quadruple the radiation of some of the lower radiation zones on Mars, for example, at the bottom of the Valles Marineris. And galactic cosmic rays, of course, are going to be splitting through the aluminum and creating further X-rays and more radiation. But things get much, much worse if we're talking about what's called a solar particle event or a solar storm. There are 2 types of these storms, one of which is called a coronal mass ejection. These are gradual. You have a lot of time as far as warning is concerned, and it takes a considerable period of time for the charged particles to reach Earth or a spacecraft or anything else, so you'd have a great deal of time to get into a solar shelter. However, if you are exposed to a solar flare, those are much more impulsive and don't offer as much warning. We're talking lots and lots of radiation here. You could absorb anywhere from 0.4 to 0.8 grays worth of radiation in a single day from one of these events. Now, once again, we're transitioning to grays because we're talking about damage to human tissue and the side effects, in other words, radiation sickness that you might get from an event like this. 0.4 to 0.8 grays in a single dose is not that horrendous, but if we're talking about a multi-day storm, the astronauts are most probably dead. They would start experiencing hair loss after about day 2 or 3. After about day 6, they would take a dose that would most probably kill them within 30 days, a 50-50 chance of that, and then after 10 days, assuming that they were unlucky enough to encounter a storm that lasted that long, you would have a 99% chance of death. And not a pleasant death either. So we definitely need very good shielding against these sorts of events. We've of course heard about solar shelters, storm shelters, that sort of thing, but they're going to have enough space, enough supplies, and just enough conveniences to survive in a very uncomfortable and packed-in environment for the number of days that the event might last. Wandering outside the shelter is a very good way to condemn yourself to a slow, lingering death. So these shelters are going to have a lot of protection. But fortunately, there are ways to handle that. But first of all, what about nuclear propulsion? Why is that advantageous? Well, because out of the 3 factors that can reduce exposure to radiation, time is the one that we can control. We can't control distance. The distance to Mars is always going to be the same, at least if we're leaving during the appropriate launch window, and we can't control these particle events, these various events that might increase the amount of radiation that astronauts are exposed to, but what we can control is the amount of time and duration that the journey might last. And with a simple nuclear thermal propulsion system, like we're going to be testing out in 2026, you could reduce the time of that journey down to 90 days instead of 6 months, which of course reduces the radiation exposure by 50% and also the chances of encountering a nasty solar storm by 50% as well. And in case you need a quick refresher, nuclear thermal propulsion, all it does is superheats the propellant, hydrogen in most cases, and then accelerates it out the nozzle of the rocket twice as fast as propellant gets accelerated out during a chemical reaction, therefore providing twice the delta V and reducing the transition time to 90 days instead of 6 months. With nuclear electric propulsion, you're utilizing nuclear power to provide electric fields or electromagnetic forces that drive ionized particles out the nozzle at a much higher speed than nuclear thermal propulsion can, achieving even greater delta V and greater efficiency. Either way, we can definitely get to Mars faster than 6 months and therefore reduce exposure times. And by utilizing small modular nuclear reactors like the ones that they're building in Sizewell in Suffolk, and also modular reactors that my daughter's working on as well in the midst of her study to become a nuclear engineer, there are many ways to deliver this kind of power in a small and compact package without having any sort of radiation danger. The same sorts of shielding that we've used on nuclear reactors to keep reactor workers like Framrick safe for many decades can also be implemented on a nuclear Starship. Really, the radiation from a reactor is not going to be much of a problem compared to the immense amounts of radiation that astronauts are going to be exposed to on an interplanetary journey. But time is one thing that we can control, shielding is the other. And the very same thing that provides excellent shielding against radiation at the nuclear reactor in Sizewell also provides the same sort of protection against radiation in interplanetary space, and that is water. Now, in Suffolk, they need several meters worth of water in order to provide adequate protection. You wouldn't be able to do that on a spacecraft, but you could probably get half a meter worth of water just from the basic water supplies that you would need for a 90-day journey or a 6-month journey or whatever. You would need that water anyway, and you could put the tanks on the outer skin of the ship to provide the necessary shielding, and as I said before, it would soak up the radiation without becoming radioactive itself. It wouldn't be dangerous for the crew to consume it after it had provided the necessary shielding. So this was one of the best solutions, would be a multi-tiered armor consisting of water and stainless steel. And to provide additional protection, you also might want to line that stainless steel with Vectran, which is a sort of Kevlar. Does that sound familiar? Well, it should, because that's what Sierra Space uses for their inflatable life habitat. Multi-layered Vectran, which provides much better protection against radiation because it doesn't create that same sort of phenomena when galactic cosmic rays pass through it, splitting off the component molecules into X-rays. That doesn't happen as much if you have a multi-layered fabric as opposed to steel or aluminum. And by the way, this is what they should be using on the Lunar Gateway. Sierra Space proposed this sort of system to NASA, but they went with conventional space station modules instead that are going to provide a lot less shielding against radiation. Why they did this is anybody's guess, but I hope they get a clue at some point and start using a module that's better suited to interplanetary travel and living in interplanetary space. And this applies to Starship as well. As I said, lining Starship with Vectran and water tanks would provide excellent protection against radiation, although you would still need a better and more resilient solar storm shelter for those solar particle events. And of course, even with all of these precautions, it's still best to reduce the time frame that you're going to be in interplanetary space as much as possible. So nuclear thermal propulsion is going to be at least the initial solution, although I feel nuclear electric propulsion, such as the one described by the guys at Mag Drive that I interviewed not long ago, Oh, you didn't see that interview? Well, you'll get another chance. It's linked at the end of this video, but in any event, that is going to reduce transit time even further. The less time we spend in interplanetary space, the better, because frankly, interplanetary space is poison for human beings. It's poison in terms of microgravity and the long-term effects that has on our muscle mass and our bone density, and of course the radiation that will slowly kill us the longer we're exposed to it. As a matter of fact, if an astronaut wants to be involved in multiple interplanetary missions, the only way that he's going to be able to realistically do that is if we implement a more effective radiation shielding system and a faster method of transport. Fortunately, we are working on both, and both need to be implemented before Elon Musk can even think about sending human beings to Mars. Hit that subscribe, smash that like, and check out the description for various ways to support my content. Thanks again to Framrick out there in Suffolk in his very remote habitat where he works on nuclear power to provide clean energy for the future of Britain. I wish him every bit of luck in his future endeavors, and as always, stay angry about space!